Yeah, thank you for inviting me to your colloquium. My goal of today is to introduce the topic of my PhD to you. I've only started in September, so it's still quite a new topic for me as well, but I'm excited about it. And my PhD is a part of a larger research project with the title High-Dimensional Expanders and Katz-Moody-Steinberg Groups. It's a cooperation between the University of Ghent and the University in Louvain-la-Neuve. And it's the three professors in the project are my advisor Tom de Met from Ghent. Then we have Pierre-Emmanuel Capras from Louvain-la-Neuve and Timothy Marquis, also from Louvain-la-Neuve for a part. And then we have, I think, 3 PhD students and 2 postdocs, all trying to construct high-dimensional expanders using Katz-Moody-Steinberg groups. And my talk has 2 main parts, and if we have time, also a third small part. First, I will introduce expander graphs, so the kind of one-dimensional object that has been widely studied and has very interesting properties. In the second part, we'll try to generalize it to a higher dimensional version. And if there is time, I want to give an example of a Katz-Moody-Steinberg group and show our idea of constructing high-dimensional expanders. So when non-mathematicians ask me to say, what is your PhD about? I'll start with trying to explain an expander graph, of course, not by saying, well, we look at expander graphs. I'll say, imagine a train network. So we have a country or a continent. We have different cities in that continent. And, well, for each city, we'll draw a point, a vertex. And whenever there's a train line connecting 2 cities, we will draw a line between the dots. And, well, that means we can travel by train from one vertex to the other. So our edges. And, well, if you now imagine you are the one who's supposed to construct the train network, what do you want from your network? Of course, you want to be able to go from each city to every other city. So it should be kind of connected. We can travel everywhere. One more thing is, I mean, train lines tend to break down every now and then. So what we don't want is a situation like here. If this train breaks, if this track breaks because of whatever reason, then those 2 big parts of the country will be separated and we won't be able to travel from one to the other. So this is something we kind of want to avoid, that every train goes through one track only. Then you might think, okay, let's just connect all the cities by a train line. Then we don't have that problem anymore. But of course, train lines are expensive, so we also want to keep the number of connections, the number of edges small. That's really the intuition between the backstory, basically, and expander graphs are now exactly the mathematical models for these good train networks, in a sense. Yeah, so let's get a little bit more formal. We'll say G is a graph with some vertex at V and an edge at E. And I will always assume that it's finite, so we have finitely many vertices. We will always assume that G is connected. Otherwise, it does not make too much sense to talk about expanding properties. I will allow for self-loops and multiple edges. So they are OK. I mean, of course, coming back to the train network, of course, it does not make sense to have a self-loop there. I mean, we can do it. It's just not very useful. So most likely they won't appear much, but it just makes it easier for construction later on, where we don't have to be that careful in the construction. That's why. And yeah, one last thing, we want the graph, also again to make life easier, we want the graph to be deregular for some natural number d, and that just means that every vertex has degree exactly d. So I don't know how, I mean the degree, so the degree being equal to d just means any vertex has exactly d neighbors in the graph. I mean, this graph that I draw here is not deregular, but yeah, we can just add a few edges and to make it regular. So that will definitely make, so adding a few edges will not make it a less good expander. And we'll see later that bounding the degree is a good way of saying having not too many train lines, because then at least the number of edges compared to the number of vertices is bound. Yeah?
So it's a fact that you can always take a graph like with the first, let's say, 3 conditions and add edges to get deregularity.
Yes.
For some.
Especially if we allow for self loops.
Yeah, I was thinking.
Then,
but then
or multiple edges, I mean, it's definitely not a problem.
A self loop counts as 1 or as 2?
True.
Good question. I would say it counts as 1. But I honestly haven't thought about it too much.
What's your definition?
That does give irregularities for counting properties for connections and stuff, right? Because normally any edge gives 2 connections. So self edges would then be half edges.
It won't be a problem later because we just count edges between different sets of vertices. So we will never count self loops. Honestly, everybody always assumes that it's deregular, and everybody says, well, without loss of generality, we just assume it. Nobody ever explains why. So I would, since we just have to change a little bit, it should not be a problem in the general setting.
Thank you.
All right. So now we kind of want to formulate what it means that we have a good connectedness, or that we have no critical edges in a way, so we don't have a bottleneck, some people also like to call it. And how do we do that? Well, we look at partitions of our vertices. We divide them into set S and set T. And then in this case, we can see there are many edges in set S, many edges in the set T, but only one edge going from set S to set T. So that's something we want to avoid. On the contrary, if we, for example, look at this, if we would choose this as T and all the others as S, we still have only one edge connecting those two sets. But then also the set T prime is very small. So this is still kind of okay for us, because it's only about one vertex that is not that well connected, but we're not really separating 2 large sets. And to formulate that, well, first we'll write EST for the set of all vertices where for all edges, where one vertex is in S and the other one is in T. And then we want to look at the number of vertices between set S and T and compare it to the size of S and this and the size of T. So if one of them is small, this quotient might still be big. If both S and T are large, the quotient, and we have little connectedness, the quotient will be small.
And
Yeah?
Are we going to do this for general subsets S and T, or specifically for sets that form a bipartition?
Yes, we will only take those where we have a partition of our vertices. And since we have that if this quotient is large, it's good connectedness. If it's small, it's bad connectedness. So we take the minimum over all partitions. And this is what is called the Cheeger constant of the graph G. So really compare, look at all the different partitions and how well are they connected with each other. And then if the Cheeger constant is not too small, it means that we don't have these bottleneck situations. Yeah, this is already enough to define what an expander graph is. Yeah, G will always be this graph. I will not write it down all the time. So G is called an NDC expander. So we really need three different parameters where, so the number of vertices has to be equal to n, G has to be D regular, and the Cheeger constant of G has to be bound from below by C. And then we call it an NDC expander. So far, so good. We can surely write down the definition. The question is, can we check the definition nicely for graphs? I mean, for a small graph like that, no problem. But if they get really big, I guess looking at all partitions can be kind of tedious. Luckily, there's another way we can describe expanders. Maybe by looking at the random walk on a graph. So random walk basically means we have, I don't know, I like to think of a drunk person walking on our graph. And in each time step, the person just randomly chooses one of the three neighbors and walks to that neighbor at random with like equal probability for all outgoing edges. And well, for the random walk, imagine we still have this graph. We start our random walk somewhere maybe here in the lower half of the graph. We'll have to go, it will be kind of unlikely that we'll end up in the upper half, because we would really first have to go here and then really choose exactly this edge to get up there. So, and we said this edge is exactly the problem why this will not be an expander. So we can also say, if we have an expander, we know that these bottleneck situations don't appear. And this implies that our random walk, we say it mixes quickly. So that means if you start somewhere at random and you just go for a few steps, it's already you have a good probability that you could end up everywhere in your graph. So that's another important property of expander graphs. And whether a random walk mixes quickly or not, in that sense, is related to the spectrum of the random walk matrix. This is what I want to introduce next. G, well, that is, we'll call it sometimes R of G or just R, and it's a matrix indexed by all the vertices of G. So for each pair of vertices, we'll have an entry in our matrix. And this entry is exactly the probability that when we are standing at V, that the next step in our random walk will end up in W. So it's the number of edges from V to W. Since we might have a multigraph, we'll write this. So this can be 0 if they're not connected, can be 1, can be a higher number, and we divide by the degree of V because that's the number of choices we can make. And since we're making life easy talking about the irregular graphs, I mean, we can just divide by D. And for people who know the adjacency matrix, this is then just the normalized adjacency matrix of G. If you don't know the adjacency matrix, you can take this as a definition.
That's for the case where we never have multiple edges, or no, the adjacency also counts.
The adjacency can also count multiple edges. It's really, yeah, it still works. Okay, and now we have this matrix, and there's a very, I don't know, a very non-trivial theorem, the so-called Cheeger inequality. That connects the Cheeger constant to the spectrum of the random walk matrix. So R is our random walk matrix, and and it has eigenvalues lambda 1 up to lambda n, and we arrange them in decreasing order. It's a linear algebra fact that the largest eigenvalue will be equal to 1. It's basically, if you take the constant vector, it will be an eigenvector to the eigenvalue 1. You can just check it because R is a probability distribution, so the sum of the values in each row is equal to 1. Yeah. Then we can really bound the Cheeger constant once from below by d over 2 times 1 minus the second largest eigenvalue, so really the largest eigenvalue minus the second largest. And we can bound it from above by d times square root of 2 times, again, 1 minus lambda 2. So this largest minus second largest eigenvalue really appears a lot here, and it deserves its own name. That will be the spectral gap, or you can say it's the normalized spectral gap because we're looking at the random walk matrix and not at the adjacency matrix. Yes?
Is it immediately obvious why 1 is the first eigenvalue and the largest, or does this require some more complex?
No, that's, why it's the largest, I'm not entirely sure, but you can see that 1 is an eigenvalue because
all ones?
It's the sum over in each row will be 1.
Yes,
and you take the constant vector, constant all ones vector as an eigenvector.
Okay.
Then it's an eigenvalue to show that it's the largest. I think you need a bit more trickery. It's not difficult, but It's like looking at this. Look at, or R, like for vectors x and yeah, the Rayleigh quotients, and yeah, I'd use some results there to get this. Okay. So yeah, maybe first let's note that okay, the Cheeger constant being bounded from below is kind of the same as saying our spectral gap is bounded from below, and it's kind of the same as saying the second largest eigenvalue is bounded from above. I mean, the constants, we might have to multiply by some constants, but if we say that 1 is definitely larger than 0, for example, then also the other two will definitely be bounded. I mean, this one will not be bounded away from 0, but like they will be bounded by some constants. And this gives us corollary. So any deregular graph on n vertices is an n d over 2 1 minus lambda 2 expander. So every connected deregular graph is an expander. Wait, there is a bracket missing.
Is there any way to see this lambda 2 vector?
What do you mean?
I mean, the eigenvectors is simply giving some coefficients to the vertices, right? And yeah, why somehow? I mean, there is a special choice of those coefficients that make this inequality happen. Where is
it's definitely not trivial to prove it. Like it takes 2-3 pages. Like with all the background work, it's 2-3 pages. I did it once in a discrete mathematics course, but I don't remember the details, honestly. Yeah.
Actually, the weights are is sort of the probability to go the next one or something. But why the second?
Yeah, it's really, you will take vectors, yeah, that are like, I'm not sure again, but you will have vectors where you have like some values, 1 if your vertex is in S, and then maybe -1 if it's in T, something like that. And you multiply it with you look at the Rayleigh quotient, and see some.
It's sort of the work that is more likely to happen, taking outside the one that has the lambda 1 equals 1, or something like this. Like if you do a million random walks,
Yes.
sort of the one that passes the most should be the one.
Okay, so we've seen every graph is an expander for a certain constant, and we can calculate the constant using linear algebra. So what now? So what we're actually interested in is not one expander graph, but infinite family of expanders. Yes?
Yeah, so if you were to, for example, do this with a graph with just 2 points and just one line between them,
Yes.
then the random log matrix would be just 2 times 2 matrix with zeros on the diagonal and ones on the off diagonal.
Yes.
Which has eigenvalues 1 and -1?
Yes, because it's a bipartite
Right,
graph.
okay.
Yes.
So in that case, the gap would be 2. Yeah, okay. Yeah, okay, I was confused. For a moment I was thinking it was going to be 1 and 1, and then I didn't see how that would have been 0, but no, it's because it's -1. Okay.
So then the h is 1.
The h will be 1, yeah.
Well, the left side would be d, and the right side, and d.
No, but this 1.
D is 1, and the left side would be 1, and the right side would be 2 times, not 2 to the 4, but 2d2. No, it would be a number between 1 and 2. But probably you can just directly compute it to be, well, I don't know, 1 maybe.
Okay.
Yeah.
Let's
I
see.
think 1.
Yeah, right. This only one set.
Yeah.
Just these
So let's look at what is a family of expanders. All have we have a lot of graphs. Such that the number of vertices in the graph will tend to infinity. I mean, we have some bound on the degree, so each GI will be D regular. And they are all expander graphs with the same constant C, strictly larger than 0. So in particular, this Cheeger constant does not tend to 0, but it's always strictly bounded away from 0. That's what we need here. And if the number of vertices goes to infinity, but the degree always stays the same, that's kind of how we get very sparse graphs that are still well connected because of our condition on the Cheeger constant. And these families of graphs have a lot of applications. Except from being interesting mathematical objects where the random walk is nice, we have nice graphs. We can really use them people use them in computer science for different constructions. One is to construct error correcting codes. So it means, I don't know if you want to send a signal to some faraway place, and on the way the signal might get some error because your cable is not perfect or whatever, and so you want to encode your message in a way that the receiver, even if the signal is a bit tempered, can still read your original message. And this, it's a lot of linear algebra over finite fields, I think. And you can really use families of expanders to construct nice error correcting codes.
Can I ask you something?
Yeah.
The upper bound.
Yes.
Is this effective? There is always a graph that has equality there?
I don't know.
Okay. We don't know about existence of graphs having HG.
Like reaching this bound. No, I don't know. Sorry. Let's come back to some application. We can use families of expanders to get so-called super concentrators, which are basically a model for really good networks. So it's, yeah. Also, something nice, and there are like several other applications in computer science. where they really use families of expanders. Okay, now I've defined family of expanders. I said they are useful, but do they actually exist? The answer is yes, they exist. It's not too hard to prove using like random methods. If you generate a deregular graph at random, chances are very high that it will be a good expander. The problem is this existence proof does not help for the applications. For the applications, we really need this construction that really tells us what are the vertices, what are the edges, how can we implement it into the computer, whatever. So we really need actual constructions, and that's where group theory comes in. Because groups can be really nicely used to construct graphs. Maybe you've heard of the Cayley graph before. I will do a bit more general definition, namely of a so-called Schreier graph. For that, we want gamma to be a finitely generated group. S should be one of the finite generating sets, and S should be symmetric, meaning that any inverse of an element in S is already an S. So it's like the generating set, and we want the subgroup H of G. What? Yeah. Oh, yeah. Indeed. Here. Cool. And then the Schreier, sometimes it's called the Schreier coset graph. So I mean, it's a graph, and it has vertices, exactly the cosets of H in gamma. And well, as edges, we have that two cosets are adjacent if and only if we have some generator in our generating set such that, well, they only differ by multiplication with S, those two cosets.
What do we mean by a finitely generated set?
A generating set. Yeah, I agree that using the same abbreviation for different words is a bit tricky, but yeah, it's just one set. So, quick example: if this subgroup is trivial, then we get Cayley graphs, in case you've heard of them. And I don't know, another easy example. Take gamma to be the integers, H to be 5 times the integers, and S 1 and minus 1. What do we get? So the cosets are just the elements of Z mod 5Z. We get 5 of them. And generating set is plus or minus 1. So if I'm at 1, it's connected to 1 by the plus 1 action, connected to 1 by the minus 1 action. So we get the pentagon as our Schreier graph here. Oh yeah, I wanted to introduce a notation. So we'll write G for graph, the group, the subgroup, and the generating set. And this is really the tool, or one very useful construction to get a nice graph, because now we can really use properties of the group that we know, and they will reflect in properties of the graph that we get. Has anyone heard of Kazhdan's property T? No? Okay, that's unfortunate. I will not define it, but I will use it. Regarding the construction of families of expanders, there is a big breakthrough theorem that was first used by Margulis. I think in the formulation, I want to write it down, was given by Allen and Millman. And let gamma be a discrete, finitely generated group. Discrete means we look at it as a topological group with a discrete topology. I mean, we have S is our finite generating set, and it's symmetric again. And we need a whole sequence of subgroups. And okay, they should be finite index so that our Schreier graphs will be finite. And I mean, we want that the size of our Schreier graphs increase and go to infinity, so the index of the subgroups in G should go to infinity. And the theorem says, now if gamma has Kazhdan's property T, then our family of Schreier graphs with respect to gamma, Hn, and S, this will be a family of expanders. So it says if we have this property T, and we have some finite index subgroups, so we have a generating set, then we get this infinite family of expander graph. Now you might ask yourself, what is property T? I'll not define it because it would take like 10 minutes to go through the definition, but it's a property of so-called locally compact topological groups, and it's about their unitary representations. for example, SLN over the integers for n greater or equal to 3 has property T. SL2 over the integers does not have T. Yeah, no. And there are many other groups that have property T. There are many groups that don't have it. It's really just a property that is connected to these unitary representations. And somehow these unitary representations of a group are related to the expansion properties of the Schreier graph. It's a quite, fascinating relation. Again, 2-3 pages of proof with the, you basically have have to read like 30-40 pages of a book to get to the point where they will prove this theorem. It's quite involved. Theorem, and this property T also has a lot of other applications, like some relation with amenability and property T. They have some, work together, and it appears in other very group theoretic areas. But it's also connected to this very combinatorial notion of expander graph, which I think is quite fascinating. Okay, I see I only have 15 minutes left. I wanted to give you the first construction of expander graphs, of families of expanders, but I think I will skip that so that we can actually go to the higher dimensional case. Okay. So how do we generalize graphs to higher dimensions? In the graph, we had vertices, dimension 0, points. We connected these vertices with lines. So dimension 1, we always have 2 vertices in one edge. And what happens if we say, okay, what do 3 vertices span? They will span a triangle. So we also look at triangles. But then we don't stop there. We can see what do 4 vertices span? A tetrahedron. So we also consider tetrahedrons. And what do 5 vertices span? Some 4-dimensional objects. We also look at those, and so on. And we can also glue several of those objects together. For example, like that. So that's the intuition between our generalization, and this will give rise to the definition of a simplicial complex. I'll mostly write SC for simplicial complex. And for that we need V, a set of vertices. For the definition of a simplicial complex, it doesn't have to be finite. For our application to high-dimensional expanders, it will always be finite. So for me, it's finite. And X will be a collection of subsets of V. So some subsets such that, I'll write it here, 1, well, each vertex has to be an X, or more precisely, every singleton set of the vertex has to be an X for every vertex in our vertex set. If this is not the case, we'll just have to change our vertex set, make it smaller. And 2, which is maybe the more important condition, is that if we have some element A in X and a subset B of A, then that already has to imply that B is in X. So I don't know, if you look here at the example, we have that this tetrahedron maybe is in our simplicial complex, but then also all the triangles, all the faces have to be in the complex, all the edges and all the vertices that are in it have to be in X itself. And in particular, the empty set also has to be in X. So this is our generalization. Yes?
So what is the relation between simplicial complex and simplicial set? So these give rise to simplicial set, but not all simplicial sets are like this.
What is this simplicial set for you?
We can talk about it after then. Yeah, we can talk about it after the talk then. Yeah. Sorry.
There's also a different way to, I mean, not very different way to generalize graphs, namely hypergraphs. I don't know if you've heard of hypergraphs. Okay, then don't worry because they are only a special case of simplicial complexes anyway. Okay. I don't know. Yes. Okay. Let's continue with our simplicial complexes. We need a few more definitions, properties of those complexes to be able to define what we mean by an expanding simplicial complex. Anyway, first of all, if we're given any element in X, I will sometimes call them faces or simplices. That always just means an element from X. We can, well, associate a dimension to it. I don't know, if you think of the triangle, it has 3 vertices, but dimension 2. So it will be the size of A, minus 1 will be the dimension. For any dimension k, xk will just be all the faces with dimension k. Note that by this definition, the empty set has dimension minus 1. So that's also possible. What else do we need? So we call X is a pure n-dimensional simplicial complex if any maximal phase where maximal with respect to inclusion. So each one of those has to have dimension n. So I don't know, this example up here has dimension, is pure of dimension 3 because any vertex, edge, or triangle is contained in one of the 2 tetrahedrons, and they will be our maximal faces in this case. I don't know if I would add something like that, wouldn't be pure anymore because this vertex is not, like the edge would be another maximal face that has a smaller dimension. And from now on, any simplicial complex will be pure n-dimensional. Okay. Then we need 2 kind of substructures of a simplicial complex. One is the one skeleton. Of X. This is a graph, or more precisely a multigraph with vertices, or just the vertices of X, so they're 0-dimensional faces, and edges we will connect to vertices by as many edges as there are maximal faces in X that contain both V and W. So it's, I don't know, for the example there. Let's see, we have those edges, and most of the vertices that are connected by an edge, this edge is only contained in one of our maximal simplices, so they will be connected by single edges. And then only if we look at those two vertices, they will be contained in both maximal. So these will get a double edge here, and then single edges. I hope I got everyone. And so this is the one skeleton. And we say that a simplicial complex is connected if its one skeleton is connected. Okay, one last thing. If we have a face A, the link of A in X.
Quick question
Yeah.
about the xk. Is it the dimension of A is equal to k or most equal to k? Because
The dimension of A is equal to K. So really want the ones.
is this is not the same as the k skeleton? Then I think we've seen.
Yeah. No. Our definition in algebraic topology was all things smaller than k.
Yeah. So that is still a simplicial complex.
Yeah.
So here it's a different definition of
Yeah,
skeleton.
it spans the same simplicial complex, but
Yeah, I think also the idea here with this definition of simplicial complex is to somehow capture how well V and W are connected, like if they're really just at the side of the simplicial complex or really in the middle, covered by a lot of part in a lot of maximal faces. I think you can use your definition as well that you had, but then you need to weight your graph exactly by these numbers, and I thought this is a bit easier. Okay, quick look at the link. This will be all faces in X that you can think of. They have empty intersection with A, but a union B is another face, or you can also write it as all B set minus A, where B is a face and A is contained in B. So that's another possible definition of a link. With a quick example, we have a tetrahedron. I don't know, we look at the link of this vertex A. Then A is, you can either say, for example, in this definition, you look at all the edges that are connected to A. Those will be our vertices. You look at all the faces that contain A. They will be our edges. And then we have the tetrahedron itself. So the link will be the triangle, the filled triangle in this case. Okay. Then I want to give the definition of what is called a one-sided and the local spectral expander. This definition is due to Kaufmann and Oppenheim, and it says, so we have X a pure n-dimensional simplicial complex, and this is, I will not write it again, a lambda local spectral expander if for all faces of, so all faces of dimension smaller or equal n minus 2, the second largest eigenvalue of the random walk matrix of the one skeleton of the link of A and X, let's say one skeleton or lambda, if this is bounded by lambda. So we can really boil it down to looking at graphs. So because the one skeleton is a multigraph, so we can look at the random walk matrix, we can look at the spectrum. And this is why it's called a local spectral expander, because we kind of look at the local spectrum. There's also another theorem, for which I don't have time yet, saying that if everything is nicely connected, we only need to look at those A of dimension n minus 2. We only need to look at the links of those, because the link of A in this case will have dimension exactly 1, so that's a graph. And then it's enough to look at this, to look at the spectrum of that graph, if we know that all the links of all dimensions are connected. So that's another theorem. This is the definition of spectral expanders that is mostly used because it's somehow easy to deal with. But there are also many, many other definitions of high-dimensional expanders. For example, you can look at the cohomology of the simplicial complex, for example, over R, and you can define something similar to the Laplacian of a graph, or Laplacian of a Riemannian manifold. I think they also have Laplacians, and you can get a version of this Laplacian for simplicial complexes, and then look at the look at the spectrum of the Laplacian and say if that one has a good spectral gap. In a sense, we call it that it would be a spectral expander. And to write it down, so we have that local spectral expander implies being a spectral expander in this cohomology sense, which is very nice because it means we really just have to look at graphs to get the spectral expansion. But there are still more ways to get high-dimensional expanders. For example, you can look at the Cheeger constant and say, how can we generalize the Cheeger constant to simplicial complexes? And you can do that using, again, cohomology, but over the finite field with two elements. And you will get a different notion of high-dimensional expanders. So in the graph case, they were equivalent, but in a higher dimensional case, they're not equivalent, unfortunately. And there are even more notions. There's like a topological expander, a geometrical expander. It's like co-systolic expander, a lot of different definitions. Which one is the best one or the correct one? I mean, we don't know yet. So I think applications will have to tell which, the ones they use is the ones that we should look at, I guess. But of course, this definition is what people use most at the moment because it's the easiest to check. So this is really, what we try to construct.